this problem, we have basically 3 bags and there are 3 coin types. So, the 3 coin types are basically 9 grams, 10 grams, 11 grams. Okay. So in each of the bags, you have, many coins, and but the trick is basically each bag contains coins of one type. So basically, if you basically have bag 1, then it will only, let's say it contains 10 gram coins only, then all the coins are going to be only of 10 grams. Okay. Likewise, basically, if there was another bag, say bag 2, and it had basically 11 gram coins, then all the coins are going to be of 11 grams. Now, like I mentioned, the 3 bags, and what we're required to find out is the number of weighing on the digital scale that we have to do. So the number of times we have to weigh on the digital scale such that we can find out which bag contains which kind of coins. All right. So let's see if you can do this question. Please try to, so now is a good time to basically pause the video and see if you can do it yourself. Okay, so I hope you got to the answer. In case not, that's perfectly okay. Let's try to solve this together. And this problem, we're going to be using Pigeon Hole Principle, but in a very different way. I think it's not to solve the problem directly, but rather to understand what kind of specification we need to do. Well, and the other thing I would say is basically this question is kind of not a direct extension, but a sort of an evolution of a previous problem that we had done, which was the goal detective. So link is going to be in the description for that problem as well. I would highly encourage you to check it out as well before you proceed and try to solve this problem together with me here. Okay, so let's try to do this. And the first thing we have to understand is we'll try to progressively increase the complexity of the problem. So let's first see, let's say if there were 3 coin types. Okay, 9 gram, 10 gram, and 11 grams. And let's say if there was just one bag, right? So there was just one bag, right? And in this bag, let's say there was some kind of a coin and all those coins were of that same type. So how many ways would we need to understand what kind of coins lie in this bag? I think the answer is very clear. It's just you take one of the coins, you weigh them on a digital scale, and you will know if it's 9 gram, the bag contains 9 gram coins. If it's 10 gram, 10 gram coins. If it's 11, it's 11 gram coins in the bag, right? So just one weighing, right, is enough. And how you do it, basically just take one coin from the bag and weigh it on digital scale, right? And that should be good enough. Okay, so let's now try to understand what would happen in bag if there were 2 bags. Now the problem gets very interesting. So I would encourage you to pause the video and try to think about it, how you can solve this problem now. Okay, so I hope you got to the answer, but if not, that's okay. Okay, so here, what we need to understand is, if you probably saw a goal detector problem, you may be tempted to say, okay, take 1 coin from the first bag and 2 coins from the second bag. Well, the answer may not be correct here, because there can be a combination where you would see, you may get a non-unique answer, right? So what I mean to say is, if you look at basically 2 bags, if you look at 2 bags, what are the all possible combinations of which can happen in this setup? So let's say I say, bag 1, bag 2, right? So I'm creating, all possible combinations which can happen here. And what you see is basically in bag 1, you can have a 9. In bag 2, you can also have a 9. You can have a 9, 10. You can have a 9, 11, right? You can have a 10, 9, so on. The last one is going to be 11, 11, right? So basically there are 3 times 3, which is 9 combinations, right? So 9 combinations can happen because there are 3 type of coin types. And there are 2 bags, so 3 cross 3, right? 9 combinations. Well, let's see what are the different range of, ways. If we just have to use one weighing scale, what are the different range of weights that can be captured if we, let's say, had just 1 coin from bag 1 and 2 coins from bag 2. Okay. And, because there are 9, 10, 11, you can also represent them something like this. You can also say it's -1, 0, +1. It's on a different scale. Basically, what you have done is basically you've demeaned, these 3 numbers. Where the mean is 10, you take them out, it doesn't make sense. It's just going to make our problem easier to understand. Okay, so let's try to understand what are the ranges of weights that can be captured using these, the setup of 1 coin from 1 bag and 2 coins from the second bag. So if you see basically the lowest possible case is basically you have 9 gram coins in the bag 1 and also 9 gram coins in the bag 2, right? So in this case, you will have if you basically had 1 coin from bag 1 and 2 coins from bag 2, the lowest possible range of basically this is the lowest of range of the weight you will get. So the weight essentially is going to be -1 plus 2 times -1, right? That's -3, right? So again, -3 is what it's trying to say. It's 10 minus, it's a demeaned form. Essentially, if you had 9, it's basically 10 into 3 minus 3, and that's 27, right? But in a demeaned form, I think just for the sake of simplicity, it's easier to understand. Okay, so that is the lowest possible range. What is the highest possible range? Highest possible range is, but you had 11 grand coins from both these bags. So that's going to be then +1 plus 2 times +1, right? So that's going to be +3. So you see that basically, the actual range of weights, if you basically pick 1 coin from bag 1 and 2 coins from bag 2, is actually -3 to +3, right? So in total, you're covering 7 possible situations. So there are 7 possibilities, right? Now you have to understand, you're trying to cover 7 possibilities, but you actually have 9 combinations, right? So this is like, you have 7 holes, right? So this is like 7 holes, and there are 9 pigeons. So as per Pigeon Hole Principle, what you see is T is 7, K is 1, and you have TK plus 2 pigeons, basically. That clearly tells us that greater than or equal to K plus 1, right? Or in other sense, greater than or equal to 2 pigeons would share a hole. And now this can be more, but at least 2 pigeons, are going to share a hole, right? There's a lower limit. So now this what does it mean now here? What this basically means is you will have 2 combinations that will have the same weight here. So it's like it's a non-unique mapping. It's not a one-to-one mapping here, right? So this is the way we're going to using Pigeon Hole Principle in this case. So that's why this one weight, the 1 coin from the bag 1 and the 2 coins from bag 2 combination is not enough. Now, what do we need to do basically to make sure you cover basically 9 pigeons here and you have a unique mapping? So I think the answer should be pretty obvious here. For unique mapping, you basically need 9 combinations, or 9 for unique mapping. Basically, you need 9 holes, right? So the range of the weight which coins can capture should be covering 9 possibilities. So let's see how we can do this. Okay. All right. So for this, I propose, let's say if you take 1 coin from bag 1, and let's say 3 coins from bag 2. What do you have here now? Now the range is going to be -1 plus 3 times -1, which is -4. And the extreme positive range is going to be +1 plus 3 plus 1, which is +4. Now this is for 9-gram coins, and this is for 11-gram coins, right? And there can be other cases as well. There could be 9-10, it could be 11-10, other cases. But basically, if you cover the extremes, you will get the range. So now the range is -4 to +4. And this includes actually 9 possibilities. You're covering 9 possibilities. This is precisely what we wanted. We wanted 9 possibilities to capture basically 9 combinations. So in this case, you'll be able to capture all of these, different combinations which bag 1 and bag 2 can have, and you can uniquely capture which of these combinations is it going to be for us if we take 1 coin from bag 1, and 3 coins from bag 2, as mentioned here, right? So I hope you're understanding this, and if you're not able to follow this, I would encourage you to, pause the video and see if you can go back to the basically bag 1 case, where we had 1 coin, and then we went to the 2 bag cases, where you had you had 2 bag cases basically, where we first started with 1 coin from bag 1 and 2 coins, from bag 2, like here, right? And see what went wrong here. Why did we fail in this case? Because of the non-unique mapping. And then in this case, basically, when we switched to this mapping, when we switched to this kind of a setup of picking coins from bag 1 and bag 2, we did successfully have a unique mapping. Therefore, we were able to map all the possibilities to all the possible combinations using the range of weights which shall be captured using this combination. Okay, now let's try to basically understand what would happen in our case, which is 3 bags situation. Now again, all possible combinations of weights, all possible combinations of bags can be, so bag 1, again, 3 possibilities, bag 2, 3 possibilities, and bag 3 also 3 possibilities, right? So you basically have 3 cubed, which is 27 possibilities. 27 possibilities, right? So we need also basically, we need to pick up the coins from these three bags in a way such that when you capture the range of weights, which are captured by these coins, by the weight of these coins together, it should be able to capture 27 possibilities, right? Okay, so we see basically there are 27 possibilities. Now let's try to reverse engineer this. Whenever we pick up coins from these three bags in a fashion, their range should be able to cover these 27 possibilities. That then only will have a unique mapping from the weight range of these coins that we pick from these bags to all possible combinations of these coin types which these bags can have, right? So 27 possibilities in terms of the range. In terms of range, it should be from minus 13 to plus 13, right? The reason being, if you basically see 13 minus 13 negative 13, there's going to be 0 in between, and therefore it computes to 27. The range encompasses 27 different values. Bag 1, we know we're supposed to pick 1 coin. From bag 2, we're supposed to pick 3 coins, right? Now, and when you basically do this, so bag 1, 1 coin, bag 2, 3 coins, we already know the range goes from minus 4 to plus 4, right? In order to get basically minus 13, we need to basically have something, and we need to basically add a number on both sides. So let's say for minus 4 plus x is equal to minus 13. So clearly we can see that it's minus 9, right? And on the positive side, 4 plus x is equal to 13. We can also see x is going to be 9 here, right? So I'm just trying to figure out what number should we add on the both sides of the extremes of the range so that we can cover minus 13 to 13, right? So basically we see we need something of 9. The number is going to be 9, right? So what are we supposed to do? What we would do is basically we would say, let's say from bag 3 we pick up 9 coins. All right, and see, this is how I'm trying to reverse engineer. I see what kind of values I should be adding to the extremes, and then I figure out, okay, if I need minus 4 to go from minus 4 to minus 13, I need minus 9 to be added there. And to get minus 9, basically you would need 9 coins, because when 9 coins would be from 9 gram type, that's only when you're gonna get minus 9. And similarly, when the 9 coins from bag 3 are gonna be, let's say 11 gram types, you could get a plus 9, right? And assuming bag 1 and bag 2 also have 11 gram coins, then plus 4 can go from plus 4 to plus 13. Okay, so okay, so let's see now how this distribution is, what kind of output it gives us. So what you see basically, let's say bag 1, bag 2, bag 3 are all from 9 gram types. So you see minus 1 plus 3 into minus 1 plus 9 into minus 1, and that is going to be minus 13, right? So if all of them are 11 gram types, what is going to happen? It's going to be plus 1 plus 3 into plus 1 plus 9 into plus 1. That's plus 13. So we see the range go from minus 13 to plus 13. Okay. So this basically covers 27 possibilities. And in this fashion, basically, you can uniquely capture which of these, if you pick up these coins from these three bags in a fashion and then weigh them on a digital scale, you can map them to the kind of combination you have across these three bags, right? Combination of the coin types. So in this fashion, you just need one weighing, right? You just need one weighing, but to find out the bag type, and the number of coins you're going to pick from each of these bags is going to be 1 coin from bag 1, 3 coins from bag 2, and 9 coins from bag 3. Okay, similarly, basically, if you increase the complexity of the problem and say we have 4 bags, then in this case, basically the number of coins you need from bag 4 is going to be 2 raised to the power 4 minus 1. This is basically 3 raised to the power 3, which is 27. And as you can also basically increase the complexity further, and you will see that for 5 bags, it's going to be 3 raised to the power 5 minus 1. That is going to be 3 raised to the power 4. That's going to be equal to 81 coins, right? So 81 coins from bag 5. Okay, so in this fashion, basically, you can see how this out, the number of coins you have to increase so that, the range of the weights of these, the range of the weights, which is captured by these coins, covers all the possible types of bags that can, that can occur in our problem. All right, so I hope you got to the answer to this problem, and, I hope you enjoyed this one. If you did, that's great.